Welcome to CD Latecom video series number 5, Volume Calibration with Hypertonic Saline. In order to streamline your cath lab workflow, most centers will apply this method of volume calibration offline after the case. In summary, 2 items will be needed for this volume calibration method. The first required item is an average cardiac output value provided by some external reference, such as thermodilution or indirect Fick estimation. Note we will use this average cardiac output value later in the calibration process. However, this value is not needed during any live data acquisition. The second required item is a PV loop recording of a 10 milliliter bolus injection of 5% hypertonic saline. In fact, it's recommended that a minimum of 2 10 milliliter bolus injections of 5% hypertonic saline occurs per dataset. Recall that a dataset is defined as any single time a PV loop catheter is delivered into the ventricle. For interventions like a TAVR procedure, where the PV loop catheter and TAVR system are both delivered via the same access, one would save recordings into 2 datasets. Recordings collected during pre-TAVR deployment would be saved in dataset 1, and recordings collected during post-TAVR deployment would be saved in dataset 2. Each dataset needs to be calibrated separately, which means that dataset 1 and 2 in our TAVR example will each require an average cardiac output value provided by some external reference and a PV loop recording of a 10 milliliter bolus injection of 5% hypertonic saline. Please note that 5% hypertonic saline is the minimum concentration needed to warrant the desired effect and has recently been standardized for this calibration method. The more commonly available 3% hypertonic saline concentration will not be sufficient. This recording shows the expected PV loop changes when 5% hypertonic saline is injected. Note that the recording begins with steady-state loops. While the patient is performing an end expiratory breath hold, the physician injects a 10 milliliter bolus injection of 5% hypertonic saline over the course of 3 seconds, or 5 to 8 heartbeats. Finally, we see the PV loop shift to the right, which is a primary indicator that the hypertonic saline bolus was successful. This rightward shift is not a real change in volume, but rather an acute change in conductance because hypertonic saline is more conductive than blood. As such, the Inca system can automatically remove parallel conductance, which is a conductance catheter phenomenon whereby uncalibrated volumes are overestimated due to the contribution of anatomical structures to the conductance signal. Another way of stating this is that hypertonic saline will essentially define the physical boundaries of the ventricle, as seen in red in this schematic, and provide an accurate measure of end diastolic volume to calibrate the volume signal. Now, we will walk through how to apply the volume calibration. In this example, we've recorded 2 baseline files, a third baseline file that we named cardiac output equals 4.02 liters per minute, which was determined by thermodilution in this example, and 2 hypertonic saline bolus injections. Note that the 2 baseline files were saved as data files, the cardiac output file was saved as an SVCal file, and the hypertonic saline files were saved as EFCal files. These should be saved as such during data acquisition in live data mode to streamline the offline calibration. Open any data file to go into the study. Next, we will select the volume calibration window. By default, we will be in dataset 1 and see our data files. If the cardiac output file was saved as an SVCal file and the hypertonic saline files were saved as EFCal files during data acquisition, we will not see them listed here. Before we apply the volume calibration, we will need to go into both SVCal and EFCal files to make some final adjustments. Let's start with our SVCal file. Because we're still within dataset 1, let's choose our SVCal files by using this drop-down menu. Here, you'll see the related cardiac output calibration file listed. The first thing we'll do is enter the cardiac output value, determined by some external reference, within the cardiac output reference column. In this window, the reason why we typically name this file cardiac output equals the value is so that one does not have to remember what this value is when inputting the reference number. Likewise, if I didn't have this pre-recorded, one can always make a copy of the baseline file and name it cardiac output equals whatever. After inputting this number, be sure to checkmark the file so that these average values populate here. Next, we will analyze the hypertonic saline recordings as EF-Cal files. By double-clicking on a file, we will see the perceived increase in volume, which is used to determine an EF-Cal value. These beats in red are automatically detected by the software and encompass the increase in volume resulting from the hypertonic saline bolus injection. Notice we have two values here, an EF and an R value, which are correlation coefficients. The EF value pertains to the rise in end diastolic volume defined by the green line on the beat-to-beat recording, and the R value pertains to the rise in end systolic volume defined by the magenta line on the beat-to-beat recording. We aim to have a number higher than 0.8 for each. Here, both are above 0.95, so no changes need to be made. If we were not happy with these numbers, the automatically detected beats in red can be changed by highlighting beats and selecting either Add to or Remove from Volume Calibration Range within the toolbar. Recall that these beats in red should encompass the increase in volume resulting from the hypertonic saline bolus injection. As beats are added to or removed from the volume calibration range, BiV Conduct NT automatically recalculates EF and R values. Once EF and R values are optimized, checkmark the hypertonic saline file and double-check that the SV-Cal and EF-Cal values have populated under calculated values here. Remember that the SV-Cal and EF-Cal values are not direct measures of stroke volume or ejection fraction. Rather, they are volume calibration values that vary based on catheter type, electrode spacing, catheter positioning, and other factors. I am now ready to select Apply. After selecting Apply, users will receive confirmation that the volume calibration was successful. A successful volume calibration will also be demonstrated by opening a baseline file to confirm that our red volume signal and PV loops have turned blue. Once blue, we are ready for analysis. In summary, the two items during the intervention that we need are 1. To take note of the cardiac output value determined by some external reference, and 2. A recording of all hypertonic saline bolus injections. Again, that's 10 milliliters of 5% hypertonic saline. If the dedicated cardiac output reference file and hypertonic saline files were not saved as SV-Cal and EF-Cal files during data acquisition, these will need to be changed within the volume calibration window. We will then view the SV-Cal file and input the cardiac output value determined by the external reference into the cardiac output reference column. Likewise, on the EF-Cal side, we will look at the hypertonic saline files and confirm that the EF and R values are greater than 0.8. If less than 0.8, you can move the end systolic and end diastolic markers and/or choose to add or remove beats from the volume calibration range to improve these values. Finally, confirm that both the SV-Cal and EF-Cal values appear at the bottom of the volume calibration window within calculated values before selecting Apply. After selecting Apply, your PV loop should turn blue for any data file within that dataset, indicating you're ready for analysis.